Hello, PCS 211. So in this lecture, I'm just going to introduce a new concept, which is the concept of momentum. And I'm going to go through some of the basics of the theory of momentum and what it is and sort of how it can be changed and how it's related to force and the things that you know before, Newton's second law, for example. And then I'll go through some examples and some conceptual clicker questions during the lecture. So I'll basically go through this lecture in some detail now, and then we'll work out the details of the example problems and the clicker questions during class. Okay, so this is the lecture on impulse and momentum, starting chapter 9 now in the Surway and Jewett textbook. So let's get started. So the purpose of this lecture, as I mentioned, is to introduce a new concept, which is the concept of momentum, and how it's related to force, which is something that we already have talked about. There's this other quantity which we're going to encounter called impulse, and I need to explain what that is and how it's related to the change in momentum. And then we'll talk about how to calculate both the impulse and the change in momentum for a constant force and for a varying force. So this should remind you a lot of like work and energy. You know, we thought about like how do we calculate the work done by some force for a constant force and for a force that changes with time. And this is going to be quite similar to that, except we're not calculating work, we're calculating this thing called impulse, which I will explain what that is. It's related to work, it's kind of similar in some ways, but it's not exactly the same. Okay, so whenever I mention the word momentum, I always ask my students in class, like, where have you heard momentum? What does momentum mean to you? It's something that we hear in everyday life. And so what does it mean to you? Usually I get analogies for sports. So people say, like, if a team is on a roll, they have a lot of momentum. Right? They're kind of like hard to stop once they've gotten going, right? The other place that it shows up is in politics. For example, everybody talks about who has the momentum going into the election. They're kind of like, you know, on a roll. They're kind of moving very well towards the election. So we have like, you know, these are old articles. This is from Joe Mentum, was from the 2004 New Hampshire primary for the Joe Lieberman, who ended up getting 5th out of 5. So Joe Mentum ended up being something that was kind of the opposite of momentum. There was Mitt-mentum, which is Mitt Romney was saying that he had Mitt-mentum. That also didn't turn out to be the case. Very recently, we had an election in the US, and we had another Joe. So we had Joe Mentum. Biden sweeps with Joe Mentum. This time he did, in fact, win. And the other one, this one doesn't really work, but people say it anyway, Trump-mentum. Anyway, so everyone talked about momentum in politics. So what does it mean in physics? What is momentum? Momentum is, it's related to mass and velocity. So it's a very simple formula. P is equal to m times v. So P is momentum, mass times the velocity. Couldn't be simpler. Make sure that you are aware that momentum is a vector, right? So I've got the arrow on top of the P and the arrow on top of the V. V is a vector, as you know, right? So the direction of the momentum is the same direction as the velocity. The units of the momentum, if you can just look at here, it's the units of mass times the units of velocity. So it's kilograms times meters per second. And unlike, you know, the units of energy is kilograms meters squared per second squared, we call that a joule. There's not really a special name for momentum. We just usually write kilograms meters per second. Okay, so there's not a new special unit name for momentum. Okay, what does momentum have to do with things that you already know? Going back to Newton's second law, which was, you know, possibly one of the most important equations in the course, the sum of the forces is equal to the mass times the acceleration. You can see that momentum doesn't show up in there, so what does momentum have to do with this? In fact, if you go back to Newton's original writings, you can read it, and actually he talked about momentum, or they say he talked about momentum. If you actually read it, which I would not recommend, if you read Newton's works that he actually wrote, he says, here's law 2. The alteration of motion is ever proportional to the motive force impressed and made in the direction of the right line which that force is impressed, which is hard to understand, right? I mean, this is a long time ago, several hundred years ago. So to us, that doesn't make a lot of sense. But the people who are experts in this subject, who have like studied Newton's writing and are familiar with the language at the time, tell us that what he's actually saying is F equals the change in momentum. That's the net force is equal to the rate of change of momentum. Okay, so this is how Newton explained his second law, which we now know as F equals ma. But he was actually saying that sum of the forces is equal to dp dt, the rate of change of momentum. And I'm going to show you now that that's the same thing as F equals to ma, okay? So when you see this, the net force is equal to dp dt, that's really just another way of writing Newton's second law. It's another way of writing F equals ma, but in terms of momentum instead of in terms of mass and acceleration, okay? Here's a proof that this is the same thing. So let's take, let's suppose I have a system of multiple objects, m1, v1, so let's say m1, mass 1 is moving at speed v1, mass 2, velocity v2, and so on, right? So I've got a system of a bunch of objects with different masses and different velocities. So I want to use Newton's second law for this system. Let's start with this. The external force is equal to the change in momentum, the rate of change of momentum, the net force. So that's d by dt, that's the derivative of the momentum, which is m1 v1 plus m2 v2 plus m3 v3, so on. So this is the p for the system, right? Total momentum for the system. Now that derivative, I can take the derivative of each term separately. So maybe the first term I'll write like this, m1 v1, like that, right? But the m is a constant, so it can come out in front here. So m1 times d by dt of v1, and the derivative of velocity is acceleration, okay? So in this first term, I have m1 times derivative of v1 with respect to time, and that's m1 times a, right? And this is m2 times a. So you see that m times a is showing up here because the derivative with respect to velocity is equal to acceleration, right, ma. The interesting thing about this formula that is written here, the way that Newton wrote it, is it's more general, actually. You can see here it works for a system of a bunch of masses. So I can have a bunch of masses, and I can still use Newton's second law here. And the other thing is that this is actually true even if the mass changes. You know, when I use F equals ma, the m has to be the same throughout the problem, right? The mass can't change. But if I write it this way, F equals dp dt, the mass could change, and this is still valid. So this is the most general form of Newton's second law, F equals to dp dt. And it's sort of a little less familiar than F equals ma, but still completely true, always true. You know, one of the most important equations in the course. So it's a law of nature, it's always true. So just to re-emphasize, F is equal to dp dt. This formula is true even if the mass of the system changes, so this is an important equation. And if you're wondering, this ext means external force. So it's the force from the outside, right, of the system. It can't come from inside of the system. It's a force from something outside the system. Changes its momentum. Okay, so let's take a look again at that equation. This is the one from the previous couple slides, which is also Newton's second law. It just looks a little different. It's not F equals ma, but it's the same thing. And let's imagine that we have a constant force. So let's focus on the case now where we have a constant force. Then that derivative, I don't need the derivative, I can just do like delta p divided by delta t, right? Now this thing, if I take this delta t and I move it to the other side, I have the equation on the following line. I have F times delta t is equal to delta p. Okay? So all I did is rearrange this equation here and put the delta t on the left side. So the net external force times the time interval over which it acts is equal to the change in the momentum. That's what that says in words. This thing the net external force times the time here has a name, and it's called impulse. Okay? The impulse is of the net force, is another way of saying it. Okay. So what is impulse? 3 equal signs means a definition. So I'm defining this thing called impulse. Impulse is a vector, and it's equal to the net force times the time over which it acts. Okay. So this is the impulse of the net force. It's the net force applied over a time delta t. Okay? And that's what we call impulse. And the impulse is equal to the change in momentum. All right. If you look at the units, the units of impulse are force times time. So that's Newton times seconds, which you can write as kilograms meters per second, which of course is the same units as momentum, which has to be the case for the two sides of that equation to be equal. So if I have impulse on an object, I will change its momentum. And the impulse is the net force times the time over which it acts. Here's a clicker question, which I won't work out now, but we'll do in class. What net force is needed to stop a 2,000 kilogram truck traveling at 25 meters per second in the positive x direction in 10 seconds? Okay, now this question you can probably do using kinematics and things like this, but I want you to try to do it the new way using momentum and impulse. So think about going back to this slide, what is going to be the change in momentum, what is going to be the impulse, and that way I can determine the force. So try to do it this way, not using kinematics. Okay, we'll do this one in class. All this stuff should remind you of work and energy. So let's go back and review a little bit from last week. The net work, we said, was the net force dotted with the displacement. So work is a force over a distance, right? F dotted with delta R. And the net work was equal to the change in the kinetic energy, right? Remember, kinetic energy is 1/2 mv squared. So there's this thing called work. Work was a force applied over a distance, and the net work was equal to the change in the kinetic energy. Now there's another thing called impulse, which I just defined for you. Impulse is the net force applied over a time. And the impulse is equal to the change in momentum. Okay? So they're like sort of related. They're both forces acting over some distance or some time, and they both change some like motion of the object, but what exactly they change depends on which quantity you're looking at. Work is the net work is equal to the change in kinetic energy. The impulse, which is the force applied over the time, is equal to the change in momentum. Okay? So make sure you get these straight in your head. Don't confuse work and impulse, and don't confuse kinetic energy and momentum, right? Those are different things. In particular, they're different because, impulse and momentum are vectors, but work and energy are scalars. They don't have a direction associated with them. Okay. Here's another clicker question. A constant force is applied for 2 seconds to change the particle's velocity from v1 to v2. Determine the force applied if the mass of the particle is 2 kilograms. And there's some choices there. Again, don't use kinematics here. I want you to use impulse and momentum. And we will work this one out, or give you a chance to vote on this one during class. Just remember, when you're thinking about this, we got to think about the momentum as a vector, right? So if I want to know the impulse and the force, I need to remember that momentum is a vector and take into account the fact that the direction of this object has changed. Okay, this formula here is the formula for the impulse from a constant force only. So far, going back a couple slides, everything I've talked about so far was a constant force. Okay, assuming the force never changed. Well, what if the force does change? We learned something similar to this when we were talking about energy. Work is force times distance, but only if the force is not changing. If the force is changing, I needed to make a graph of force versus distance and calculate the area underneath that curve. The same thing is true for impulse. So impulse is a force applied over a time. And in this graph here, I'm showing an example. So this would be the net force applied over the time. And you can see like it starts at 0, and then like the force gets bigger and bigger and bigger and bigger, and then slower and smaller and smaller and smaller and smaller. So the force changed throughout that time interval. How do I calculate the change in momentum? I need the area underneath that curve. So the total area under that curve will correspond to the impulse applied to the object, and that will be equal to the change in momentum. It's the same idea as calculating the work done for a varying force. The work done, we were calculating the area underneath the force versus the distance curve, right? This was x, and I had something which changed like this. The area was equal to the work, right? If I instead plot force versus time, then the area is equal to the impulse. Suppose you have a changing force, like the one that's shown on the left there, and you want to know what's the average force that was acting on the object. What you can do is you can replace this changing force with a constant force, provided that the constant force changes the momentum by the same amount as the changing force. So what I need is, if I want to make it an average force, I want to figure out what's the average force during this time interval. Of course, it's changing, right? It gets bigger and then it gets smaller again. But what's the average force? The average force is defined to be something which is constant. So you can see this average force here is constant, it's flat. And the value of that has to be chosen so that the area underneath this curve is the same as the area underneath this curve, okay? Then I would say that this constant force would be sort of changing the momentum by the same amount as this varying force. Okay, so that's what I mean when I say, you know, if the force is changing throughout the time interval, I can say, but what was the average force? The average force is going to be the constant force which changes the momentum by the same amount, and that corresponds to this area being the same as this area. Okay. All right, so with that in mind, here's another clicker question, which I will just like present to you here, and then we'll do it in class. So suppose in 30 seconds, one person named Tyler throws 10 tennis balls at the wall. Each has a mass of 0.6 kilograms, 0.06 kilograms, and a speed of 20 meters per second. And you know a tennis ball, it's going to go and hit the wall and bounce back, right? At the same time, another person named Sarah takes the same 10 balls of putty, which have the same mass and the same speed, and those stick to the wall. Okay, so some of them, the tennis balls are bouncing off the wall, and the putty is sticking to the wall. And I have a simple question for you, which is, what is the average force on the wall, or how does it compare for those two students? In other words, do those over 30 seconds, when they've both thrown 10 of those things in the wall, and some of the tennis balls have bounced off and the putty is stuck to the wall, which one is going to be exerting a bigger average force on the wall over all 30 seconds? So we have the choices there. Tyler's is bigger than Sarah's, Tyler's equal to Sarah's, Tyler's less than Sarah's. We will discuss this further in class. Okay, so I'm going to summarize kind of theoretical considerations here, and then we'll work out those clicker questions and some examples in class. What I've given to you in this little mini lecture is that I have another way of writing Newton's second law. Instead of the net force is equal to ma, the net force is equal to dp dt, the rate of change of momentum, and momentum is m times v. We talked about this thing called impulse. So impulse is the net force times the time interval over which it acts. And the net impulse is equal to the change in momentum. If you have a force which varies with time, like in the graph which is shown there, to calculate the impulse, I need the area underneath the curve. That's going to kind of do it. I will summarize here, and we will kind of discuss some of the details and some examples and those clicker questions during class. So I hope you have found this little mini lecture useful, and see you all in class when we kind of go a little bit deeper into this topic.